I'm Heath, I'm the clean room manager here in physics, and I'm responsibility for both the clean room suite here in the ground floor and the clean room upstairs on the first floor. In this room we predominantly do processing for our substrates to clean them up using solvents in preparation for spinning on the E-beam resist. It's a plastic polymer that we use so we can write our patterns in. The kind of things that we're making here are electronic devices based around thin film materials like graphene and TMDs, though we also make photonic structures for light experiments, etc. So if we move through, we can have a look at the E-beam system, which is down the other end of the facility. So here we are in the E-beam room, and this machine here is a Nanobeam NB4. It's a dedicated E-beam lithographic tool. And what this can do is it can write patterns in the polymers that we use, which are like hard plastics, and where the electrons write, the plastic will be deformed, and then we can go through another chemical step and clean that material away. It's like developing a photograph. So what we've done now, by using this E-beam system, we've actually put a pattern into the plastic for future processing next door. This machine is highly accurate, and we can write structures down to 10 nanometers, and we can also write structures much larger, up to a 6-inch size. So this is a 6-inch chuck, and this is designed to put lots of tiny little chips on here, 5mm size and 10mm size on here. But we also have a blank version where we could put a 6-inch wafer and write a very large pattern. Once the chucks are loaded into the system is pumped down. This area is always pumped under a very good vacuum, and then we can load the individual chucks into the machine, and by using some digital software we can make digital patterns, and we can basically inform the machine to write those patterns. The patterns themselves can be very small, but also the picture is broken down into tiny bits, and all of those bits are stitched together incredibly accurately. So once we've made our pattern, we kind of work out, well, why are we doing this thing? So imagine that we're depositing a thin film material. It may look something like this. This could be graphene, and maybe this is only 5 microns big, so it's very small. So we need something that's able to write very accurately very small sizes, and we might want to shape this into a particular shape. So the first thing we need to do is to define a pattern. So if we cover this whole thing in plastic, and then ask the machine design a pattern that will actually write a pattern. Now where I write with the pen is where we can get the electron to write. And all this area, all this shaded area, the plastic chemical nature would be changed, and what we could do is take this back to the chemistry area, develop it like a photograph, put it into a liquid developer and stop. And then all of the area here would be removed, and all we'd be left with is our shape of our graphene. We remove the plastic from everywhere, and we're left with a graphene shape a bit like this. The next stage, we may want to define this shape. So our graphene is still here, remember? We've not got rid of it yet, but we've defined this shape and this box. So this area is now open. If we go next door, we can have a look at a couple of machines that will help us to etch this thing. So these two machines are reactive ion etchers, and they use a plasma generated by injecting a small amount of gas into a vacuum, good vacuum, and then we excite an electric field across the gas, and that generates plasma. And the plasma has the effect of being able to bombard the surface. So all the area that I defined earlier as being opened now will be seen by the plasma, but this area is still covered with the plastic, as is all the rest of the area. So now this plasma will destroy all this film, and we'll end up with graphene that's this shape. The next thing we can do is we can also use the E-beam lithography system to define other patterns. Imagine if we use the system to define these shapes. So here is our graphene that we etched. Now we can define these shapes, which we can open up. So now these are like opened up trenches now in the plastic that we put another layer on. we may need to put some contacts on here. So we make them with gold, very pure gold, and we use these thin film deposition systems to apply these materials. So we've gone through the E-beam system again, we've defined our pattern, we developed it like a photograph, and we can pop the samples up here like this, fix it to something inside this machine. And what this machine is, it's a thermal evaporator. And what we can do in here, inside the machine we have 4 versions of these little boats, these little dimples. We can put little pieces of gold in here. And we also use other materials like chromium to help to stick the gold. And we pump the system down to get a good vacuum. And then we can apply a large current across these boats. And the current is so high that it's high enough to melt the gold. The gold then evaporates up like a metal gas and floats up onto the sample, which is sitting up here. The gold coats everywhere, and it also sits now on the substrate surface here, but here it'll be everywhere, it'll be on the plastic itself. And then all we need to do is to put this into some acetone, and that will dissolve the plastic completely everywhere, and all the gold will lift off, apart from the areas that are now stuck to the surface of the substrate that we use, which is generally kind of silicon wafer. So now we have an electronic device, because now we can attach gold wire and attach out to the outside world, as it were. And the way we do that, we have these little tiny ceramic packages. So here's an empty one here. This is a 20-pin version. We can cut our silicon chip down to maybe 4 mil square and stick it into the bottom of here. And then what we can do is we can attach gold wire to the package surface and then loop up and join onto our gold pads here. So how do we do that? Well, we use these 2 machines. These are called wedge bonders, and they use a spool there. You can see 25 micron diameter gold wire. Just to put that into perspective, human hair is between 50 and 100 microns in diameter. So it's very, very thin wire, very pure. And this machine uses ultrasonics, so it basically vibrates the gold wire onto the surfaces that we've created here in all our processing. And then it's literally like making a weld, which is quite a strong weld. So we can connect up our package to the surface of our device that we've made. And then these packages can then be taken to the laboratories, and you can see that the pins go right through the bottom here. And they can be put into measurement systems in laboratories around physics and in engineering, and also in LSI maybe, and then they can do the measurements on them from there. We also have a couple of little other bits of kit that are useful for us. Before we get to the packaging stage, we sometimes put the chips on this probe station here, and that enables us to use the probes just to touch down, make contact with the pads, and we can supply current here to the device and measure the continuity to make sure the devices conduct electricity, and we can measure their resistance. Also, from the thin film deposition side, we sometimes would like to measure the film thickness, and we can use this little profiler here, which is able to go over steps, so it can come along and up and over, and there's a little stylus there at the back of the machine, and very accurately we can measure between 5 and 200 nanometers step heights. So it's letting us know exactly what thickness films we're depositing in our various systems. The large system here is really a very, very posh version of one of these. So this is an E-beam evaporator, and this gives us the opportunity to deposit thin film materials like metals, gold, titanium, aluminium, palladium, platinum, and niobium using a highly collimated beam of electrons, which ablate the material in the boat, similar to the thermal evaporator, and then that is deposited onto the system.